Good afternoon, everybody. My name is Felix Yanovsky, and I would like to start my presentation, which is entitled Data Fusion and Processing Tool for Comparing Rain Reflectivity Estimations using 94 GHz radar and laser disdrometer. I am representing two universities, Delft University of Technology in the Netherlands and the National Aviation University, Kyiv, Ukraine. Here is the outline of my presentation. And as an introduction, I would like to say about the problem of meteorological radar calibration, which actually appeared immediately when weather radar, meteorological radar, became to be the instrument for quantitative measurements. A lot of different kinds of weather radar were developed. Here you can see some examples of weather radars. Majority of them are of centimeter wave. So S-band, C-band, and X-band. And why we need calibration? Because in order to provide quantitative measurements, absolute calibration is necessary. And such important parameter like radar reflectivity is one of the first and the most important up to now. A couple of words about radar reflectivity. Under certain conditions, radar reflectivity, which we designate Z, can be related to microstructure of the weather object in the radar resolution volume. Starting from radar equation, we can connect the radar cross-section of the scatterers in the volume with the reflectivity, which actually is the sixth moment of raindrop distribution in the resolution volume. And this formula is valid in case of Rayleigh approximation, which is correct only when wavelength is much more than drop size, than scatterer size. The unity of reflectivity is millimeter in 6th power divided by meter in 3rd power, and in logarithmic scale, this unity is named dBz. The purpose of this paper is to introduce a novel software tool for data processing and data fusion designed to compare radar reflectivity and other characteristics of rain using W-band radar, laser disdrometer, and other instruments. And this is done for millimeter wave radars. In this case, the wavelength is up to 30 times shorter than in case of X-band and S-band radar. Here you see some examples of millimeter wave radars developed in different countries. The delicate nature of millimeter band components and the harsh conditions in which meteorological radars operate can lead to undetected performance changes even more often than in case of centimeter wave band radars. And taking into account that quantitative measurements are impossible without calibration, the system calibration is especially important problem in case of millimeter wave radar, and it is necessary to perform regular external calibration of the question arise whether it is possible to use the methods which were developed for centimeter wavelength radar to calibrate millimeter wavelength radars. What is the difference? This difference is explained in these plots, which are taken from famous radar textbook. Radar cross-section sigma of a metal sphere with radius r. See, and in a logarithmic scale, it looks like this. where we can see Rayleigh region, me region. Rayleigh region is valid when radius or diameter or of scatterer is much less than wavelengths. And here we have resonant or me region. And in case of raindrops, which have size from 0.2 to 6 millimeter and wavelengths in W band is 3.2 millimeters, in this case, this ratio is from 0.2 to 6. That is why from this to this point, and we are working in the region. That is why that Rayleigh approximation, which is used for centimeter wavelength radar, is not applicable in case of W band radar. But this is not the only problem. It is first, but also attenuation of electromagnetic waves is much stronger in W band. Components can change characteristics uncontrollably. Also, they are sensitive to temperature, and there is a need to protect antennas and radomes from water layer. First, then I will explain the processing algorithms. I would like to say a couple of words about multi-instrument measuring facilities which are available in the Delft University of Technology. This is the building of the Geoscience and Remote Sensing Department where I work. This is the Electrical Engineering, Mathematics and Computer Science building. And here, not far from our building, is some small radio range, which is equipped with W-band radar, centimeter, 3 centimeter wavelength radar, X-band radiometer, weather station, dysdrometers, and other things. But this is for, let's say, training and educational purposes. And the devices which we use in this research are located in large radio range, meteorological site, which is located in 10 kilometers from Delft, in the center of the Netherlands, in Cabau. And here there are a lot of different devices, including the mast of 214 meters. And this instrument works in the framework of Ruysdael Observatory, which is a national initiative in the Netherlands devoted to meteorological and climate research. Here you can see millimeter wave radars, radiometer with weather station, and dysdrometers also are here, of course, present. Now I would like to say some details about measurement processing for radar and dysdrometer data fusion. Here you can see the scheme of the experiment which were performed during several years. Here you can see the W-band radar with vertical on the level of surface, Earth surface. This is the dysdrometer, radiometers, and weather stations. And actually, our task is to compare this data and try to provide the data fusion of different devices. We will see that mathematics in this case is much more complicated than in case of centimeter ranges. The experiments, the data were collected during 3 years, from 21 to 23, and we selected the days with rain. As an example, you can see here the November of 21 and the days with rain intensity and days. And we have simultaneous measurement of different instruments. Dysdrometer data, actually this is data about drop size distribution, drop velocity. These data are provided with every 1 minute new data. Radar gives new data every 3 seconds. Here you see the block diagram of data processing. So we have radar measurements from range beam, which is located on some height. We have radar reflectivity measured by this device. And we have drop size distribution, which is measured by this drometer on the ground level. So we need to take into account the difference in time. During this time, it can be evaporation of droplets during falling down. We should take into account attenuation in rain, and we should take into account attenuation in gases and other things. And this can be done by using additional data from weather stations, which measure temperature, humidity, pressure on the ground level, and radiometer, which gives us the possibility to estimate such data on the height. After all corrections, we can calculate drop size distribution after correction and use it to calculate reflectivity from drop size distribution data. Now we can compare radar reflectivity and this drometer reflectivity for W-band radar. And the difference between them can be analyzed, statistics can be analyzed, and it can be used for correction, for calibration, and so on. So what problems arise when we would like to implement this approach? I listed a lot of problems, but the most important are that scattering should be used instead of Rayleigh approximation, and electromagnetic radiation attenuation should be taken into account when propagating and scattering in W band. The most comprehensive information for all these things is contained in the scattering matrix for non-spherical particles in W band. In classical radar, a backscattering matrix is the most applicable. But in our case, for W band, we need also to take into account forward scattering. It is also very important. Backscattering is used to estimate the reflectivity, and forward scattering is used to estimate the attenuation in water droplets. So here you can see the scattering matrix. This is backscattering matrix, and this is forward scattering matrix, which connect the incident wave with backscattered and forward scattered waves. And H and B, its polarization, horizontal and vertical, can be cross polarization or principal polarization used. And in this case, we use just horizontal polarization for certainty, and the calculation of scattering matrix for non-spherical particle was done by Mishchenko using T-matrix method. It gives backscattering and forward scattering coefficients at different combinations of polarization. And as I have told, we use horizontal polarization. And in this case, using backscattering matrix element for horizontal polarization, we can estimate the reflectivity for each droplet with diameter d in millimeter in 6 divided by meter in third power. And using forward scattering matrix, we can estimate the attenuation by this droplet in dB per kilometer, attenuation by a single droplet. And these two expressions are used to calculate the reflectivity based on the drop size distribution measured by this drometer, including attenuation in rain. Here you can see the final non-attenuated reflectivity Z and one-way attenuation, which are calculated as the sum over the drop size distribution in dBz and in dB per kilometer. Using this data, we can represent the reflectivity with attenuation as difference the non-attenuated reflectivity, and as integral from attenuation per kilometer over the distance, attenuation by rain, so by water, and attenuation by atmospheric gas. So attenuation by water was shown in the previous slide, and here we show how we estimate the attenuation by gases. It is standard, actually, models which are approved by International Telecommunication Union. So for 94 gigahertz, we have, for example, we use this value, and for distance 250 meters as an example, we can calculate the losses in dBs for different content of water. Next, which we should take into account, is time delay influence, and this influence can be taken into account in two ways. The first, the time series measured by radar is ahead of the corresponding time series measured by this barometer because of difference in time, height divided by terminal drop velocity. And the second reason, the water of the droplet is evaporating during falling down. It is tens of seconds. And during this time, the droplet, which were here with some diameter, may have smaller diameter in the barometer sensitive place. So this correction on drop evaporation is done based on results published by Kumjan and Rishkov, and they estimated how it will be evaporated, but we need the inverse problem. So we need to estimate the diameter of raindrops in the height if by the result of measurements of drop diameter on the ground level. And for this, we use the coefficients which can be calculated based on the data of radiometer and weather station for pressure, temperature, humidity, and so on. Time delay can be estimated by using mutual correlation function between the series of radar and the barometer data, and the difference between 0 and the maximum of correlation function can be used as time delay. So all these mathematical models have been used to develop the software tool with friendly interface for data processing, and I will explain now it and show some calculation results. Here you can see the interface of our software. Here we can select this barometer data file, and now I will show some results. Here you can see this barometer data and radar data. They are similar, but a little bit similar, but very different, because here you see 40 dBs and here you see 20 dBs. It is data which is provided by this barometer itself using its built-in. Here, after calculation, according our algorithm, we have this red curve, which is around 20 dBs already, and here it is represented. Now you can see we can include drop attenuation. It is different, a little bit smaller. We can include gas attenuation, again smaller. In order to see difference, we can zoom. Now here it is some peak, and if we put filtered droplets bigger than 6.5, these peaks disappear. And now we have also correction on evaporation. Also, it is the difference with zoom. And radar data can be a little bit averaged, and we can combine them in united plot, and you can see the difference in time. We can calculate difference in time. It is 61 seconds in this particular case, and after correction we have quite similar results. Radar data are a little bit more practically always. This is easy explained because radar is sensitive to small particles, and this barometer is sensitive only to the particles which is more than 0.2 millimeters. And here it is a spectrum, this barometer and radar spectrum. Difference is because of resolution, because this is 3 seconds, this is 1 minute resolution, and scatter plots for reflectivity, for mean velocity, and for Doppler spectrum width. In radar case, Doppler spectrum width. In case of the barometer, just spectrum width, velocity width. And based on this result, we can say that our software works properly, and radar and the barometer data are fusion, and both instruments are very glad because of that. And this is a time to think about the conclusions, and the conclusions are following. The method of multi-instrument W-band radar calibration has been analyzed in detail. The issues and their solutions have been discussed. The convenient, friendly software has been developed for comparative analysis of the huge database which contains W-band radar and laser barometer data. Experimental part of the research is based on multi-instrument measurements provided during several years in the Cabau experimental methodological site in the Netherlands. The specialized MATLAB software tool for processing, comparison, and fusion sophisticated multi-instrument data has been developed, tested, and used as the tool for correct comparison of radar reflectivity factor, Doppler spectra, mean and root mean square velocities. And finally, I would like to mention that this work was supported by the Netherlands Organization for Scientific Research grant. Thank you.